Hi, everybody. I'm just getting things ready so that we can take a look at our next unit. In Unit 6, Chapter 5, Statistical Reasoning, what I'm going to be looking at in this particular video is Section 5.4, where we took a look at normal distribution. Now, the objective of what we were trying to accomplish was to go through the idea of normal distribution so that you would understand its properties. What do we mean when we say that something is distributed normally? And then we took a look at that data and started to be able to analyze things and take a look at what they mean when we talk about normal distribution. So, vocabulary terms that we wanted to look at, make sure that you're watching for the words normal curve and bell curve, that you're familiar with what those mean, and then normal distribution. The first exercise that we did in class together was involving some dice. And I asked you the question to start off with. If we rolled one dice 50,000 times and recorded the rolls that we got, I got a 6, I got a 4, I got a 2, I got a 1. And then I asked you to take all those results, to imagine taking all those results and putting them in a frequency table, and then take your results and put them into a histogram. The question was, what would your graph look like? What would the histogram look like? Well, most people came to the conclusion that because there's no higher probability that we're going to get a 6 versus a 1 or a 2 versus a 3, chances are that the histogram data that we would have bins or towers, if you want to call them that were pretty close to the same height. So then we looked at it and said, well, okay, what happens if you roll 2 dice and you record the sums that you get and check to see what happens then when you take your data and put it in the histogram? So now clearly imagining what that looks like is a little tougher, and certainly doing it 50,000 times is very monotonous. So what we did instead was, with your partner, you rolled 2 dice 50 times. You recorded the sums and then took that from your frequency table and made a histogram. So many of you would have had results similar to something like this, which is what I did when I tried it. So you'll see the number of times that I rolled the following sums, and then I created my histogram to begin to demonstrate what my material looked like. Well, we took a look at everything that everyone had done, and then we talked about, well, what would it look like if we combined everybody's results? And what we were finding was that everybody had low results on the sides and that there were higher results in the center. And so, what would happen if we put it all together? Well, then we tried it, and we actually used a dice simulator online to be able to test our predictions. And if you have any desire to play with that a little bit, here's the website or the link that you can use to go and do it yourself. But then we actually took some pictures. So if I rolled one dice 50,000 times, this is what it would look like. So you can see I have exactly 50,000. You can see that my towers are almost exactly the same, and certainly from a distance, they look pretty level. They're not exactly, because this is raw data, of course, but it's pretty equal across the board. And then if I did it with 2 dice, what was the result? And I got this very interesting pattern, this sort of gradual stair steps right to the center where I have the 7 and then back down again. And so we discussed, well, why is that happening? Well, certainly the numbers on the edges, the 2s and the 12, we know that there's only one possible way that I can roll a 2 and a 12. Whereas for the 7, there are a variety of different ways I can get a 7. And so it meant that there were more opportunities for me to get a 7 than the 12 and the 2, and so on down the line. So then I asked the question, well, what would happen if you made it 3 dice? And so we tried to play around with that a little bit, and then we tried it on the simulator and found out that it creates the same shape, that there are certain combinations that are more common and there are others that are more infrequent. And you create this sort of shape that you have kind of starting low, coming up to the top, and then going back down again. So really what's happening here is as the number of die increases, the curve becomes smoother. So if I would go back to that picture for a second and say, well, what if there were 4 dice or 5 dice or 6 or 10 or 20? Well, we're going to have the same shape, but just smaller towers. And as you have smaller towers, these little steps are getting closer and closer to a smooth curve. So we say the curve is getting smoother. Well, it turns out that this shape that we have generated by just rolling 2 dice or 3 dice or more is called a normal curve. It's sometimes also referred to as a bell curve. And this is a symmetrical curve about the mean. In other words, where the mean is at the center and it's symmetrical on either side, we call it the normal curve or the bell curve. Now, the cool thing about it is that many physical quantities in real life are distributed this way. If we collect data on a variety of different things, collect a bunch of data about something, put them into frequency tables, and then put them into a histogram, what is very, very cool is that the normal curve comes out in many of these instances. Things like the heights of women or the heights of men. Here's a graph that shows you the heights of American women from ages 30 to 39, and you can see the normal curve emerging. We can also do the very same thing with the results from exams. So if we took all the exam results for standardized tests and put all of those grades into our histogram and drew a graph, we would create something that generated the normal curve again. This is a graph showing the SAT scores, the mean and standard deviations are given. And it's giving us some information, but the cool thing about it is that it is the normal curve. You could also do it with the heights of people, heights of women, heights of men. If you took all that information and graphed it in the same way that we did with our information on the dice, we would get the normal curve. So it all boils down to the following, that data in a histogram or a frequency polygon that results in a symmetrical distribution about the mean is said to have a normal distribution. Now, an important question, where would you expect to find the mean, the median, and the mode in a normal distribution graph? Well, if you've been paying attention to the definitions we've used, you would expect to find all these three things right in the center. The mean, median, and mode are equal, pretty equal, and in raw data, sometimes they're a little bit off, but they're close. And they are found in the exact center of the normal distribution graph. And then the rest of the data is spread out on either side according to the standard deviations from the mean. So if you have the mean and one standard deviation above or below, two above or below, the data is stretching out underneath, on top of those particular standard deviations in mean. Now, the question is, if I change the standard deviation, so if I make it longer or shorter, what happens to my curve? Well, if you spread out your data by making a higher standard deviation, what happens is the data kind of gets stretched out, and so the curve gets flatter. So it will be more spread out. If you take a look at the following diagram, you'll see this happening. You can see that all three of these normal curves have a mean of 100, but their standard deviations are different. The red one has a standard deviation of 20. The fuchsia colored one has a standard deviation of 10. So it's not as spread out. And then the one in the center, which is blue, has a standard deviation of 5. So it's a really close standard deviation and a really high curve. This is a similar diagram, actually, but I wanted you to see it because of the green one. So yes, it's a normal curve. It's shifted over because the mean has been placed over at -2 instead of at 0. Now, there's an important clarification that's due to be had right here, and that is about the way in which we indicate the symbol for mean. You know already that we've seen on our calculator that when you calculated the mean on a set of data, that this symbol indicated that it was the mean from the sample. But literally, this is described as a sample from a population. Now, when it comes to normal distribution, we're going to be using a different symbol for mean because it symbolizes a population instead of the sample. Now, all that sounds very confusing. And at this stage in understanding statistics, you don't need to know anything more than that this symbol means the average or the mean of data, and so does the X bar. And when we're using normal distribution, you're going to see this one popping up a lot more in the diagrams and illustrations that we use. So the values numerically are the same. The mean is the mean, whether it's the sample or the population. but just beware that this symbol is going to pop up now. Okay, let's go back to our work. A very important property of the data that we're talking about. Now, think back for a minute of what we did with the dice. We rolled it 50 times. We recorded how many times we had the different sums, put that in a frequency polygon. We created a histogram to show our results. And then 100% of our results, so all of that data, created a very rough sketch of the normal curve. But it turns out that every normal curve you have, that the area under the curve is always equal to 100% of the data in the data set. So if you think about what 100% means, it means the whole thing. And 100% is 100 out of 100, which is really just 1. So we can say it's 100% of the data, or it is just 1. Now, the other perspective on understanding the normal curve is that it actually gives us some information about the probability distribution. And so what that means is if I look at this lovely normal curve and I've got my standard deviations, 1 above and below, and 2 above and below, and 3 above and below underneath my curve, what I could say is that the amount of data that's distributed within one standard deviation of the mean is a big chunk. It's a big portion of the area of the data. And then I could also say that pretty much all of the data is distributed within 3 standard deviations of the mean. Now, those words describe what I see in my graph, but they're not very numerical. And we're going to come up with specific numbers. How much of the data is here? How much is here and here and here and here? And it turns out we can measure that. So let's try it first of all. See if we can come up with some numbers that are close to these standards percentages. I'm also going to need to look up something as I go through, so I'm going to try and talk while I'm moving some papers around. We're going to look at some examples that we had on your classwork page that you used in class together. And what we had was a normal curve. You can see it right here on some graph paper. And what we're going to do is try to figure out how many squares are there actually located within 1 standard deviation and 2 and 3 and so on. So first of all, one of the things we had to look at in this particular example was we've got all these little squares. And I need to know, okay, I know that the area underneath this curve is 1, but what I'd like to really know is how much of the area is this little square? Now, I think you're all right in me saying that, well, from here to here is 0.2, because this is 0.2, 0.4, 0.6, 0.8, 0.10. In other words, 1. Sorry, shouldn't be 0.10, but it is 1. So this is really 0.2, which means this guy is 0.2 as well, which means the whole area inside of here is 0.04. So if I take the area, which is 1, and divide it by the area of little squares, I find out that there are actually 25 squares under this curve. So now, if I've got 25 squares under the curve, let me count how many there are between -1 and 1. So the standard deviation, 1 below and 1 above. So I count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if I go up to the next row, I can see 11 and 12. This is pretty close to 13 and 14. Maybe I could use those little tiny guys. So that's 13, 14. This one's getting, well, it's pretty close, like a 15, 16. Here's like half, a 17. It's somewhere, if I kind of smudge things together, I think about 17 is pretty good. And if I think, what's 17 out of 25 squares is a percentage of 68%. Okay, so roughly, I've counted the squares. I have about 68% of the squares within 1 standard deviation of the mean. And then it says, do the same thing, but do it with the 2 standard deviations. Okay, so if I start with 17 squares, which I had here, let's count some more. This would be 18, 19. Now this guy's getting pretty close, 19, so that would be 20, 21. And then you've got like 22, 23. You're getting pretty close to 23 going on to 24. Now, if you measure those percentages, 23 out of 25 and 24 out of 25, you're getting somewhere around the 95% mark. Okay, and then if we think about 3 standard deviations, within it, you have pretty much all the data. It isn't all of it because the truth of the matter is this line comes down really, really close, but it never actually literally touches. It gets very close, but doesn't touch. So it's almost 100%. Almost 100%. Okay, so then we tried this one, and then we tried it one more time with another one. Now, this one is a little bit of a higher curve. You can see that your standard deviation now is just 0.5 instead of 1. But we did the very same process. We know that the area under here is a 1. And so we look at the area of this little square. We know that from here to here is 0.25. So 0.25 times 0.25 is 0.0625. And if I divide that into a 1, I find out that there are about 16 squares under this curve that I have. So we're going to do the very same thing we did before, and we're going to count them up. So let's see. For the first standard deviation, it's just to the 0.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm getting, well, this isn't quite 11. It's more like 10 and a half-ish, well, almost 11. So let's say it was 11 out of 16. And so 11 divided by 0.16 gives me 68.75%. So I'm pretty close to what I was with the other graph that I did before. And then if we do the next one and do 2 standard deviations, then I've got, let's say 11. So then I do 12, 13. And then I've got 14-ish and 15. We're looking at pretty close to 15. And if I do 15 out of 16, I get 94%. And then the last one, of course, is what would it be within 3 standard deviations? And you can see, look, it's pretty much all of it. There's just the tiniest squeak that's not there. And so if I use that, it's almost fully 100%. Okay, so these 2 examples are sort of a demonstration of what we're going to look at next, and that is what the literal amounts are. Just like we found in our first examples pretty close, that the data underneath within 1 standard deviation added up to 68%. The data within 2 standard deviations added up to about 95. We found 94, but it actually literally is 95. And for the 3 standard deviations, it's 99.7. It's almost 100%. Now, we find that the best way to memorize this is to break this up into sections. And so we're going to do that. And I would ask you to make sure you label your graph. This is 34, 34. 13.5, 13.5, 2.35, 2.35, and these tiny little parts on the end are just 0.15%. Notice as well that the notations underneath here are kind of interesting. This one, of course, is the mean. This is the mean plus 1 standard deviation, the mean plus 2, the mean plus 3, and you'll see that they've labeled it. It's kind of a neat way to label it, and just be aware that those are there from time to time. Okay, so now it's time to actually try some examples. So the first one, Giselle is 168 centimeters tall. Now, in her high school, boys' heights are normally distributed. This phrase is key to this question. There's no way that you can use the normal distribution percentages unless you know that it's normally distributed. So, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6. Now, in the classwork that I gave you a graph that looked like this one. And when you do your homework, I'm going to expect that you actually draw one yourself. You just need to get used to drawing this. And what we're going to do is label. That means that the mean is 174. To find this one, I'll take 174 plus 6, and then plus another 6, and plus another 6. And then I'll go minus 6 and minus another 6. And so we'll get numbers that look like the following. All right, now the question, I guess it was back in the last screen, was what is the probability that the first boy Giselle meets at school tomorrow will be taller than she is? Remember, she's 168. So here is the spot where the 168 is popping up for the boys' heights. So all the guys on this part of the curve are going to be taller than she is. Now remember, we know these percentages. And so if you look at mine, you'll see it actually when I wrote it down. So I wrote 34, 34, 13.5, 2.35, and there's also the 0.015. That should be, oh yes, I forgot. When I did mine, I actually I put zero point 0.5 instead of 0.15 here. So this number actually turns out to be 84%. So it's an 84% chance that she'll run into a guy when she runs the first thing in the morning that is taller than her. Next one. A sparkly cosmetic powder is machine packaged in a process that puts approximately 50 grams of powder in each package. Now, just like we discovered with those packages of sunflower seeds, just because it says there's 50 grams does not mean that there are 50 grams. And sure enough, the actual masses have a normal distribution with a mean of 50.5. So the average have more than the 50, but there's a standard deviation of zero point 0.5 on either side. So the manufacturer wants to ensure that each package contains at least 49.5 grams. So what we do first of all is take their graph and label it. And then we think, okay, they want to make sure that they have at least this much. So the question was, what percent of packages do not contain this much powder? So we're looking at the tiny amount right here. And if you use your own drawing, you know that this is 2.35 and this is 0.15. So about 2.5% of the packages that come out of their factory are not up to standard in terms. And that, I suppose, is for them to just consider, is that a good enough margin of error or do we need to improve it? Okay, that was the end of our first lesson on normal distribution and taking a look at normally distributed data. There's a lot of information in this lesson on the properties of normal distribution, and we had a little bit of a chance to practice some of those questions, so you'll be able to refer to these in your textbook and give them a try. I think so that this video doesn't become too terribly long, I'll stop here and then I'll do a part 2 later with the other examples that we did to practice normal distribution. Good luck, everybody.